This is rather interesting and very, very different. Let me show you the eBay listing that popped up that I saw this on. It was a UK seller, and it's notable I have tried 120 volts. It does not work on 120 volts, sorry, but I bet they do a version for that. This one came from 2017 Bulb Shop. Normally I provide a link to a generic search for these. This was the only place I could find that was selling them, unless it's got some fancy keywords. But we have a lamp which it claims is, well, it's doing that dimmable retro vintage flexible LED Edison spiral filament light bulb. String of keywords, £7. It came through very quickly because it was from a UK seller. I wasn't sure what to expect here. What arrived was very, very pleasing indeed, not just in terms of the look, but also the packaging. If I just grab hold of the sides here and pull it out, it's not just in a box with all the labelling that you'd normally expect in UK stuff. Use, place, bar, restaurant, coffee, family, game room, etc. Handy. 360-degree illumination. Handier. So it comes with this cardboard skeletal frame, and then there's a sort of locking ring at the bottom that you have to unscrew to get the lamp out. Quite interesting in its own right, just the way it's a sort of half spiral, just stepped. Interesting. I should have shown that at the correct angle. There's the step for the thread. That then reveals the lamp. And if I do a scientific material test in the way that Ave would not do it, by touching it to my teeth, that is glass. That's very interesting. I love the way that the lamp manufacturers with all the glassworking skills adapted to LED. So let's plug this in and try it out. Let's bring in the flickery hoppy. So here is the flickery hoppy with its low refresh LED display. And the pink lamp holder. Let's screw this in. It does say don't screw it into the glass. Well, I suppose lots of people have done that and broken tubes in that way, like they did in the old compact fluorescent days. Plug it in. Oh, it's not super mega bright. The display says 4 watts almost on the button, 29 milliamps, 0.563 power factor, which isn't the worst power factor. It's not great. That looks all right. I've done some initial tests on this. I put a diode in the series to see if it would still light, because if you do that with a capacitive dropper, it may light very dimly, but not very bright at all. Very dimly, but not very bright at all. Because the only current will get through is the discharge resistor across the capacitor is the only bit that will leak the current through. In this case, it did light on that halfway supply, so I think there's a bridge rectifier and regulating circuitry, and it made me think of this. I've already, in fact, oh, hold on, let's see if it's the same filament here. So that would go around like that, and then it would go around like, oh, actually it's quite hard to shape. And then it would kind of go back. It's roughly the same filament. Okay, so let me explain how they do this. This is a glass tube, and they've threaded the filament through. Goodness knows how they thread it through. I can see a slight dustiness on the surface. I'm guessing they used maybe a light powder to actually get it through, because it's quite sort of clingy. Let me tell you about this and how it works, and then we'll open this lamp up and take a look inside and see if the drivers are similar to this one. I could have powered this filament. Let's zoom down onto the bench. Let's give it something decisive to focus onto. Let's stick this down here, focus down onto there, because that's where all the action's going to be. That way I don't need to swear at the camera quite as much as normal. Let's stuff these wires into these inappropriate speaker terminals of the happy. And I can tell you the circuit board that I took this out of, it was one of those sort of spiral Edison-y look filament lamps, with the first one that came out, the flexible filament, which I promptly took apart. If I plug this in, keeping my fingers well away from everything, it just lights, and you can see a slight shimmer actually. I didn't see a slight shimmer in that. That's interesting. But it's completely and utterly flexible, quite a high voltage across this, so I'll not finger the ends, but you can see it is rubbery and flexible. Really nice, interesting material. Also 4 watts, just slightly above 4 watts. Amazing power factor. 0.9 for the power factor for this, 18 milliamps, super. Ultra efficient. I know why that is, but why? What's in there then? That's just kind of knocked me off balance here, because I thought it was going to be the same circuitry, but it's clearly not. I'm guessing little switch mode power supply now, but it does say dimmable, I think. Okay. But the science behind these LED filaments is this. I've already done a little doodle. I shall bring my doodle in. Doodle. Let's tame this down just a little tad. If you were to look end on this material, you'd see that it was basically a circular cross-section with a circuit board material going down the middle and the chips mounted on one side. I think they're just mounted on one side. Yes, they are. And the chips fire the light out, but it also bounces around and it ends up stimulating the phosphors on the other side, and the circuit board material is sort of translucent anyway, so it ends up lighting all around that. Now, if we use traditional LED filaments, do I have in the vicinity? Yeah, I've got a broken one in the vicinity. Oh, here we go. The normal LED filament has this little tiny substrate. In this case, it's ceramic. But they've got the LEDs mounted on one side of it and then phosphor on both sides. But because it's very short, they just connect all the LEDs in series like this. So it's a long series string. Quite often it's about 30 LEDs, giving somewhere between, say, 70 to 90 volts to make that LED string light, that little filament. With these, because they're having to spread across a larger number of chips, if you put them all in series, it wouldn't work as well. It wouldn't, it'd be far too many LEDs in series. You'd need a really high voltage across it. So what they do is they have a series of parallel circuits going along it. So they might have a parallel circuit there and there and there. And then they connect all those parallel circuits in series and use a slightly higher current. And what it means is that 1 watt sort of short filament ends up a big long filament. And because they've used that sort of flexible printed circuit board material for this, it's just super soft. It just feels like a rubbery cord and can be tightly spiraled, obviously not super tight, but you can get a good bend in it of, you could probably go 1/4 of an inch internal diameter, 5 millimeters, probably more. I'm not going to stress it. Yeah, you could probably squeeze it quite tight. So that's the science of these. But let's investigate what is in that lamp. So this is where I'm going to have to bring focus back up again. Yeah, I know it's some people find this a bit odd, but in reality, it does make the picture quality better. It does make it better video. I'm going to try. I'm going to try not to break this because I quite like it. But if I do break it, I break it. It doesn't really matter. I got it to explore. I got it so that you don't have to open yours. So if you get one of these, you know what's inside. I don't think this is going to open that easily. I have a sneaky feeling that this might be glued shut and I'm going to have to squeeze it gently in the vise of knowledge. Let me just get the vise of knowledge up. Let's strategically squeeze it like this and see if we can break that glue seal or whatever it is. We'll just give it a little squeeze. The glass may break. You can hear sort of stressed, crunchy noises. It's not doing anything. I want to tap this with a pair of pliers, but I kind of get the feeling that it's going to be quite destructive. Let's get a big screwdriver in and smack it with a pair of pliers nonetheless. Pliers, it's the new hammer. Okay, this isn't going to work. Yeah, this is not going to work at all. I'll just try and do stuff. It's not going to work because I'm going to have to go and put this into more appropriate grippy things. Oh, the plastic is actually distorting here. Let's give it another squeeze. I think there is a chance that we may... Oh, this sounds promising. Normally I'd pause for this bit, but I think, some of you do want to see what goes on when I'm doing things like this. Oh, let's give it another squeeze. It's not really obvious what's happening here. I don't think it's really mega opening. I'm probably squeezing a circuit board inside. It's probably dead now. I don't want this to suddenly ping and break the tube. That would be a shame because I quite like the tube. Right, tell you what, I'm going to pause. Oh no, don't pause, Clive. We want to see you break it. I'm going to pause while I go and get other tools. That's what I'll do. One moment, please. Okay, just as while I paused, I was looking for my pipe grips. The suitable crushing grip that they can apply is just ideal for this. Oh, that's quite promising. See how controlled they are. They're ideal for this. Let's get a screwdriver under there and prise now, because I don't want to squeeze it too much, because I'm already tempting fate with that glass tube. Let's hook this up like this. This is looking very promising. So it was glued in. There's no hope of getting that out. Oh, is that a little... Hold on. Is that soldered? Or is that just one of those little pins? Let's stick a knife into it and see if I can whike that out. I'm not sure how long this is going to take, because some of these can be quite hard to do. Let's go back to the older style, the Amtech knife. The one that comes out in a more controlled, less deadly manner. Is that just one of those little pins that goes in the top and can be popped off, or is it soldered? I get the feeling this base won't be going back together. Is that? That is solder. That is soldered in. One moment, please. I'm going to desolder that. It's out. There's not much on this. It is, in fact, not a switch mode. It is a simple current regulator. Let me find something thin that I can point at the current regulator. A universal sort of linear current regulator here with a programming resistor. So the incoming supply is going to the bridge rectifier via a fusible resistor, and the other lead here going to the rectifier, getting smoothed. There's a 1 megohm resistor here to discharge this capacitor and stop sort of ghosting when through capacitive coupling of the switch wiring. And then it's just this little component here, which I'll try and read the number off, and what looks like a 51 ohm resistor. I say try to read the number because right in the middle of the number is a sort of black dot that hides that. But let's do some other tests first. Let's put that back down there. Let's focus down on there. Let's zoom back out a bit. Let us plug that in to the hoppy again, because that suggests this might be a lower voltage filament. So before I plug that in, let's just stuff this into the terminals here. The reason that's why I'm using the hoppy at this point in time. So let's stuff that wire in there, and the resistor in here, and then gingerly poke about on these connections here and see if I can get the voltage. So I shall plug it in so it lights up. That component will get hot. Oh, it's not lighting. Uh-oh. That means I've either got a bad connection here, or I've pulled a wire right out. Let's see if I can get this to go, or have I damaged it? I may have damaged it. Oh, that'd be disappointing. Yeah, it's not lighting, right. Give me a moment, I'll see if I can diagnose this. And resume. So it turns out, while trying to pull that out, I'd broken the resistor inside the sleeve here, so I've put another one in. Let's stick that down here. Stick that down here. This time it should light, or it'll go bang, which one of the two. It is lit. Okay, so let's make sure we're zoomed out completely here. And I want to try, focus down, yeah, just make sure we're in focus before I go any further. Let's sweep all the conductive bits out of the way. Let's set this to an optimistic 1000 volts and probe without shorting anything out. At least it's not too bright this time. If I touch the wrong bits here, it won't end well. 265 volts. Okay. I'm guessing then that, so that's quite a high voltage across that filament. I shall take an image of this circuit board, and we can then reverse engineer it. We'll actually reverse engineer the schematic here. But I can tell you that the reason for the power, well, actually, I'll just do that, and then we'll talk about why the power factor is not as good as that other filament. The circuitry has been reverse engineered. Let's explore it. Let's get this light out the way. I've been running it to see how hot the circuitry gets. It's not that bad. I mean, it gets hot-ish, but not that bad. And if it got too hot, it would self-regulate. So let's take a look at the circuitry. The chip in question is a PT4515C. It's a linear current regulator that measures the current flowing through it. You can set a threshold. Is this bright enough? Yeah, I think it's bright enough. And once it gets to that level, it uses this sense resistor. It just limits the current through it. So all you have at the input, and I've drawn the other components that are in the circuit board, are the 10 ohm resistor in the input, which acts as a fuse and sort of inrush limiter. We get the bridge rectifier. We've got an electrolytic capacitor. Let's draw that as the electrolytic capacitor. Noting that this says it's a dimmable light, but having an electrolytic capacitor there is going to give it a bit of a rough ride, and that resistor is going to be a series of current spikes. Then it's got a 1 megohm discharge resistor. That's presumably just to clamp down any sort of leakage. Sometimes when you get the switch lines coming up to the light, if you don't put some small load across the circuitry, the LEDs are so sensitive that even the leakage between wires in the sort of the just capacitive coupling between the switch wires will cause it to glow very slightly. And with LEDs, it makes it very visible. I've guesstimated from the 265 volts and the current they're being run at, effectively about 6 milliamps per LED, that there's about 100 pairs. And that does tally up with this other one that I took apart. I've worked that out for that one as well. The circuitry is a bit different. This is much simpler. The reason the other one was showing so much better power factor is because it kind of cheats it, but also it's to make it more suitable for dimming. It had two regulating components in the other one. One of them was for the LEDs, but one of them was when the LEDs are off, it then shunted the current through a couple of resistors in the back, which just dissipated that as heat. And it just meant it drew current over the whole sine wave, and it just gave a better power factor, and also it allowed traditional dimmers to latch properly. So the 51 ohm resistor here, the chip starts limiting the current when the voltage across that gets to 0.6 volts. So if we do the maths, and we work out what the current's going to be, to get the current at which we're going to get 0.6 volts above that, I equals V, which is the 0.6 volts, divided by the 51 ohms equals, say, 0.117, so that's 11.7 milliamps, let's say 12 milliamps. So that's 12 milliamps that's flowing through those LEDs. If we work out the dissipation across the filament then, that would be, I'll just use this full number, times the 265 volts I measured across them equals about 3 watts. So 3.1 watts across all the LEDs. That's what the filament is effectively dissipating in this. It's not super bright. It's not as bright as a 4-watt lamp I would normally associate, one of the sort of 4-watt lamps, but it's designed for visual effect. It's not really aiming for lighting the room super brightly. It is an alternative to the very power-hungry, old-fashioned lamps that just have that orangey glow. It puts out a lot of light though. It could do with actually being reduced in intensity, so it is just a visual effect, but that's fairly straightforward. You could actually just use an external capacitor with this, it would work. So based on this, what's being dissipated across this? So if we take the mains voltage, which is 240 volts here, times, let's see, times 1.41 equals, so we're going to get roughly about, say, 338, so do we say 340 volts across this capacitor once it's being rectified and smoothed? So minus, if we make that the 340 volts, minus the 265 we're dropping across the LEDs, that gives about 75 volts across this. And this thing is actually rated for 450 volts across it. It's designed for high voltage applications. It's also designed for current up to about 60 milliamps, but the balance is how much heat this dissipates, because it does get hot. There is a little bit of heat sink on that, but if it does get too hot, if it reaches about 135 degrees Celsius, it will then automatically itself start regulating the current down to its comfort zone to avoid damage. So the 75 volts, this is dissipating 75 volts times the 12 milliamps. 0.012 times the 75 volts equals 0.9 watts, 0.9 watt dissipation. Add that to 3.1, that gives us the 4 watts that the light was drawing. It's just basically 1 watt across the regulator and 3 watts across the LEDs. Oh, that works out rather nice and round. Things worthy of note. You could just replace this with a resistor rated for, say, a couple of watts and just regulate the current down to, say, 10 milliamps or so. And that would work. But the downside of that is that as the mains voltage fluctuated, you would also get a slight fluctuation of the current through the LEDs. And it means that, well, I made a filament lamp based on a simple resistor dropper. And I have noticed that if people in the vicinity are switching on high loads in their houses and the voltage fluctuates just a few volts up and down, you can see that as a visible dip in the intensity. For what this does, it effectively just regulates that. You could emulate this with just a couple of transistors if it wasn't for the sort of thermal protection. That would make things more complicated. It's very straightforward. So let's take a look at the circuit board. There is only one slight screw up in this circuit board. It's that little line there that I put in the wrong place. Just ignore it. It's got a wee squiggle through it for a reason. The main supply comes in. It comes along this black lead via the resistor, and it comes along this white lead, and it goes straight to the bridge rectifier. It's a full bridge rectifier, as Electroboom would say. That gets rectified. That is this full bridge rectifier here, and then goes straight to the capacitor and the discharge resistor. Here is the capacitor. Ghosted here because effectively it's out of focus just because I kept everything. I even had the circuit board a slight angle when I took this picture. It's not quite as good as normal as a result of that, just because it was quite hard to take a picture of it in situ. Incidentally, it just glues on to a little pillar in here, and that keeps it central. It's a really nice design. Also notice, we'll tell you what, let's get up close to this. Do you see those little lines there? That's the heatsink in the back, those little ridges of solder. Back down to here we go, and back out we go a bit. So we have the bridge rectifier. It gets smeared the capacitor. It's got the resistor across it. Then the positive side goes straight out to the LEDs. This side is going straight out to the LED string. The negative side, this is a double-sided board. It goes onto that sort of heatsink. Now see the red outline here? That is the heatsink arrangement. Let's just zoom down that just a tiny little bit so you can actually see it all right, especially for those of you with smaller screens. So this red outline is the sort of outline of the heatsink in the back, and you can see that the tab here has these two plated through holes to couple the heat through to that. It has the 51 ohm resistor. It's got the space for another resistor so they can fine tune that value, but as it is, the 51 ohms worked out nicely for that 4 watts. But this negative track goes round. It goes to the 2 center pins, which are the common negative of that chip. That is effectively the ground of this chip. The resistors connected between the ground and the external resistor pin, the current sensing resistor here. That's the one the 0.6 volts is measured across to tell this when to start cutting back and increasing its resistance. And then the output pin goes, ignore this squiggly line here, it goes to the other LED lead, and that's it. It's one of the simplest of these type of circuit boards I've seen. It's a very neat design. It's a small enough design it will fit into many lamp holders. And because it's got that good margin around it, it's not going to short against the sides of them as perhaps as, well, this one does. This is that has the lamp. I've not opened it up yet. There is a short between one of the pins, or certainly through the circuitry. The circuit board is touching the side of this case at some point, and that's a bit of a taboo thing that tripped the RCD, the GFCI, in my house, because the fitting I tried it in had a metal housing. There's a good chance that if the fitting had just been a standard plastic lamp holder, this light would just have worked as normal. That's it. That's the show. That's all, folks. That is it. It's a neat, simple implementation. I love the glass, the fact that even here they've got a slight sort of the split plastic supports here that can move out so that it's held in place and then glued. The they're just splayed slightly. I've cracked that plastic right across the middle without breaking them. That's nice. And the hardest bit must have been fishing this in here. I wonder how they did that. Particularly given that you feel this original filament, and it is quite rubbery. How would it actually slide across glass? Oh, it's not bad, actually. But it does look slightly matte, suggesting they might have dusted it in some way. And they probably just put a fish wire through, hooked it on, pulled that filament through, and the glass tube is shaped purely to the size of this filament, which will be a standard. Well, what is the size of that? Let's get a measure in. I'll measure it in centimetres. It is about... Oop, I've hooked it on a wire. Let's say that all in, it's about 300 mil, which is about a foot. That's a nice round figure for imperial and metric measurements. So yeah, very neat. It's a nice implementation, a nice minimalist. There's no big glass globe. It is just this nice tight spiral. And they do it in other shapes as well. Now, the closest I can think that I've seen to this was the Bloomin compact fluorescent lamp. The Bloomin was a light-fitting, a compact fluorescent lamp that was, it's kind of designer. You see it in a lot of coffee shops where it's got the base and then it's got a couple of sort of looping tubes that then sort of interleave like that. And each one, there's two drivers inside, two ballasts, and the tubes are driven separately because occasionally you see one half completely out. And they just, instead of, trying to do what most compact fluorescent lamp companies do, of having it zigzag up, down, or spiraling round and round to try and save space, they just went for this, let's not save space. Let's make it look quite stylish with this shape. I don't know if they ever really introduced any more products, Bloomin. I know they were sort of angling with various neon benders to design them new shapes, but I don't think anything ever came of that. But their approach was, it's a lot more expensive than a traditional lamp, but you do get that interesting shape to look at. And I suppose that's the sort of same style here, that because they can do it, they have done it. So it's very neat. I like this lamp. It's very stylish. Now I'm going to have to try and rebuild it into another base or something. But yeah, very interesting. Well worth taking apart.